All right. Good morning. Good morning, everyone. Welcome to Ohio Rock Talks on this Earth Science Week. Today we're going to be talking about monitoring Ohio's dynamic geology, talking about groundwater and seismic activity. Chuck Salmons is here to help out with some Q&A, and we are going to talk to hydrogeologist Krista Hardin and geophysicist Daniel Blake. They're going to talk about the Ohio Observation Well Network and the Ohio Seismic Network, and the important roles each play in Ohio's geology. So if you have any questions, oh, by the way, I'm Stephanie O'Grady. I forgot to introduce myself. If you have any questions, you can type them in the Q&A and we'll bring them up as we get them, and we'll save some time at the end for that as well. So I'm going to hand it over right now to Krista to get us started.
All right, thank you. Let me start sharing. All right. Can you see everything? All right.
Yeah, I think we're good.
All right. So my name is Krista Hardin. I am a geologist with our groundwater division here at the Ohio Geological Survey. And so I'm going to talk a little bit about our groundwater observation system here in Ohio. So this week is Earth Science Week. Today, the theme is Earth Observations Day. So there are many ways that we observe the Earth, both scientifically and in our everyday lives. Some scientific systems in place include things like aerial imagery, weather radar, seismic equipment, precipitation gauges, satellite imagery, observation wells, stream gauges, and there are many more. It's not limited to just what you see here on this slide. But today we're going to talk about two of those systems that the Ohio Geologic Survey has in place. So I'll be talking about our groundwater observation system, and then my colleague Daniel will be talking about what the Geologic Survey does to monitor earthquakes here in Ohio. So just to start, what is groundwater? So groundwater is basically water that fills voids, such as pores and fractures in the rocks below our feet. A lot of people picture groundwater as like an underground lake, but that's not actually correct. It's more like a sponge. So a sponge has lots of pores or holes in it, and these pores can be dry and empty, or they can be filled with water. The same concept goes to the ground below our feet. So groundwater in a sand and gravel aquifer occurs in those pore spaces between individual grains of sand and gravel. It's like if you went to the beach and took a cup of dry sand and then you put water in it. That water is not going to sit above the sand. It's going to percolate in and fill up all those spaces between the sand grains that wasn't already taken up by the sand. Same thing with the bedrock aquifers. So groundwater occurs in those pore spaces, but it can also occur in things like fractures, joints, voids, and other contacts between formations, basically anywhere within the rock that rock itself does not take up space. So groundwater is part of our overall water cycle. So many of our viewers are probably familiar with the basics of the water cycle. So you've got your precipitation, which is your rain, snow, hail, anything coming from the sky. You've got transpiration, which is basically water being used by our plants and then turned back into water vapor. Evaporation, which is water turning to water vapor due to the sun's heat causing evaporation. And then condensation, which is that water vapor cooling back down to create our clouds and precipitation again. But the water cycle is a little bit more complex than that. So as that water falls, some of it's going to end up as surface runoff. It's going to end up as surface water in our lakes, ponds, streams, rivers, and the ocean. And some of it's going to infiltrate and percolate down into our groundwater. And this water, once it's in the ground as groundwater, it's not trapped there. There might be some interaction between groundwater and surface water, where a lake or a river intersects the water table, which is the level where the water is at. And also, we will bring some of that water up to use as humans through mostly water wells. So who exactly uses groundwater? Here in Ohio, about 45% of Ohioans rely on groundwater daily. That's about 5.5 million people. This could be people in cities where some of the water comes from a municipal water supply that's pumped out of the ground. Like in Columbus, there's a municipal well field. It could be individual homes that might use that city water, or you might have your own individual well at your house. It could be industries, such as factories, agriculture, so irrigation, or water for livestock. And it's also used in producing energy, among other things as well. I'm going to talk about our groundwater observation network. And this is our network of 141 wells throughout the state. And these are our observation wells. What we do is we service them quarterly, and we'll download data off of each of these wells that provide insight into what the groundwater level is doing. We'll process that data. We'll calibrate the wells as well. We'll make sure to do any maintenance and take care of our wells, and we'll do special tests and projects. And I should note that we are specifically looking at the quantity of groundwater, so the amount of groundwater present, not so much the quality. There's other departments that take care of that. Some of the locations of wells include a lot of water plants. Some are outside of factories, some are in people's yards that we have agreements with, some are at college campuses. A lot of them are just in fields, parks, basements of government buildings. We've got one at the London Fish Hatchery. So they're in all sorts of places throughout the state. And if you're like me and you grew up in the city, you might not know exactly what goes into creating a well. So I'll talk about a little bit about what is a well. So I'm going to start with our aquifer, and that's going to be the rock unit that's going to produce our water. We're going to drill a hole down into that aquifer, and we're going to put in a casing. And today, most of the casing is going to be either PVC pipe or some sort of metal, such as stainless steel, that's going to go all the way down into our aquifer with a well screen at the bottom. And the well screen is like the casing, except it has a lot of little slits that help the water get through, but keep out sand and other muck that you don't want clogging up your well. Around the well screen, you'll put in a sand pack, and that's going to help keep some of the other finer sediments from getting into your well. It'll settle those out. You'll fill grout in around your well, and that's going to keep it nice and sealed and in place, because the hole you drill is going to be bigger than the casing you put in, and you don't want your well to be crooked. You want to keep it nice and straight, so you'll put in a grout that'll keep it secure. And then most importantly is your water. So the water in the well is going to remain at a static water level. So the static water level is a level at which the water in the well rests naturally. So if this is the well for your house and you go to do the dishes, you turn on the faucet, the well is going to start pumping water, and that water level is going to drop temporarily. As soon as you're done doing the dishes and you turn the faucet off, and you're not using water anymore, that water level is going to go back up and reach that static water level and remain at that level. So what we do is we record the static water level in our network of wells, and it'll change over time. And we'll get a graph that looks something like this. So this is our hydrograph for a well that we have in Franklin County. It's for the 2019 water year. And when I say water year, you may notice that the graph starts on October 1st of 2018 and goes through September 30th of 2019. This is because October tends to be when the recharge period for the year begins. So we start getting more rain and snow as opposed to late summer when it's fairly dry. So it tends to be a better record keeping point than January 1st would be. This well is one of our wells that we use as an index well, meaning there isn't a lot of outside influence on the well. There isn't a lot of pumping in the area affecting it, so we can get data that's more focused on what's going on environmentally compared to a well located near a lot of pumping activity. And I'll show you a graph for one of those in a minute. You'll notice on the graph that there's an overall trend to the groundwater level. So it starts our water year at about 43 feet below the surface. And then the water level will rise to about 41 feet below the surface towards April, and that's going to be our main recharge period. And then over the course of the summer, that water level is going to drop back down as things dry out. And you notice, of course, little spikes along the way. those are mostly going to be precipitation events that are going to recharge the aquifer. And then as they settle down, you get little fluctuations. That's a lot different than our next hydrograph, which is from a water plant in Xenia, Ohio. And you can see a clear pattern of pumping throughout the year. All these little curves are going to be pumping that happen throughout the year in our aquifer. Though the groundwater level still fluctuates naturally throughout the seasons, but there's a much heavier human influence in the pattern that you can see compared to the last graph. So I mentioned special projects. We have 2 goals for our current grant. We have a grant with the U.S. Geological Survey for a groundwater monitoring network grant. So the goals are 1, to drill 2 new wells to add to the network. One of these wells was drilled down in Scioto County, and that's what the picture is from. And then the other well we drilled, I think in December, and that was up in Fulton County at Harrison Lake State Park. So we have 2 new wells in areas where we didn't have a lot of coverage before. And then our more important goal of our grant is to test each of these wells, each of our 141 wells, to be sure that they're working correctly. And then we can rehabilitate and fix the ones that aren't. And we do these tests, and they're called slug tests. There's a couple of different types of slug tests. So there's physical slugs, which we put these PVC pipes into the well, and they will displace water. They're filled with sand, so they're heavy enough to sink. We could just add water to the well, or we can use something known as a pneumatic packer, which essentially seals off the top of the well and forces pressure into the well to drop the water level. In each of these types of tests, we measure how long it takes for the water to get back up to that static water level that I mentioned earlier. So basically, it goes something like this. So we'll add a transducer, and that's a device that's going to record the water level based on pressure, water pressure in the well. Then we're going to drop in a slug. So in this case, a physical slug, which was the first example I talked about on the last slide. And as soon as we add that slug in, you can notice the water level rises and the test starts, because as soon as that water level rises and it's displaced, it's going to automatically start dropping back to the static water level. And you're going to hope to get a nice curve like this. And that's going to help show that our well is responding correctly and gives us insight into the characteristics of the aquifer. It can also help tell us if our well is not responding properly and needs to be rehabilitated. So when we're not doing tests on our wells, they're going to have something like this in place. So this is our standard setup for inside a well for our day-to-day data recording. You're going to have a battery and a solar panel that's going to keep our gauge powered. The gauge itself is this blue box, and that's going to record the water level. It does that by recording the motion of this wheel. So there's a wheel here and a metal tape on it. That tape is connected to a float and a weight down in the well. The float in the well is going to always stay on top of the water that's in the well, and as that water level fluctuates, the float will move. And as that float moves, this wheel will move, and the gauge can record the movement of this wheel. We record measurements every hour for our wells, and then we take the daily maximum to keep when we process the data for the year. We also have a couple of special wells in our system. So we have 18 real-time data wells, and these provide data in real time to us. It's transmitted via satellite, and these are partnered with USGS, and we can view these on their website, which is really convenient if we need to know something about what's going on in an area without having to drive to go and check on a well. We also have 2 special earthquake wells. So one of these wells is in Delaware County. It records some earthquake motion. And then we have another well in Van Wert County, and this records earthquakes surprisingly well. This has a special real-time gauge on it that measures levels every minute instead of every hour, unlike our other wells. And if it detects a rapid change in level, it'll start recording every quarter of a second. So this graph on this page here shows the water level in our Van Wert well on July 22nd of this year, when there was a 7.8 magnitude earthquake all the way in Alaska. And there was a displacement of about 1/1500ths of a foot, which is a significant amount, but we've actually had fluctuations recorded in this well of up to 5.8 feet in water level from larger earthquakes. Now, water wells aren't the best way to measure earthquakes because they're water wells. However, the survey has an entire seismic program that I will pass on the presentation to Daniel to talk about. And with that, we're good to go.
All right, give me 1 second and I will get your presentation ready to go here.
Krista?
Yes.
We did have a question that came in from Aaron, who is the Southwest Scenic Rivers Program Manager. He asked, regarding the Xenia Hydrograph, which you shared, would the episodic fluctuation be due to the water plant topping off its water towers or other reservoirs?
It could be. All we can tell from it is that there were pumping activities happening. But if they're going to be filling water towers and things like that, it could very well be what they were using that pumping for. I would have to ask the Xenia water plant people to know for sure, though.
Dan, can you share your content, please, with me so I can pull that up for you? Here we go, guys. Just give us 1 second here and we're all good. Dan, if you unmute yourself, you are good to go.
Okay, can you hear me now?
Yep, you're all good. Thank you.
All right, thank you. Okay, hello everyone. My name is Daniel Blake, and I'm a geophysicist with the Ohio Geological Survey. And today's Ohio Rock Talks Part 2 is going to be about seismic monitoring. So we're going to talk a little bit about that. We're also going to talk about earthquakes and how to locate an earthquake in class or at home. So an earthquake is what happens when two pieces of the earth suddenly slip past one another. The surface where they slip is called the fault or fault plane. The location below the Earth's surface where the earthquake starts is called the hypocenter, and the location directly above it on the surface of the Earth is called the epicenter. Earthquakes create seismic waves that travel through the Earth, and by analyzing these seismic waves, scientists can explore the Earth's deep interior. So what you just saw in the video to the right, which I'll replay for you, is the shaking intensity or how much the ground moved during the 1906 earthquake in San Francisco, which did a ton of damage to that area. So we've never had an earthquake that big in Ohio, but I'm going to tell you a little bit more about Ohio's earthquake history and some other exciting stuff. So here we go. All right. So before we start into earthquakes, we're going to talk about plate tectonics. So the Earth's surface is broken up into what geologists call tectonic plates. Tectonic plates are massive, rigid pieces of the Earth's crust. Tectonic plates move slowly across the Earth, moving entire sections of continental and oceanic crust along with them. So as you can see, there are a bunch of different plates here. Ohio is located on the North American plate, which is orange. So if we click, you can see that the plate boundaries can be identified where significant earthquakes and volcanic activity have occurred in the past. And earthquakes provide evidence of the plate boundaries. And in general, earthquakes occur when plates move under, over, or slide past each other. So typically we like to define them as how the plates move. So we typically see convergent plate boundaries, divergent plate boundaries, and transform plates. So a famous example of a divergent plate boundary would be the Mid-Atlantic Ocean Ridge between North America and Africa, which is spreading apart. Another famous example of a convergent plate boundary would be in the Himalayas, where you have the Himalayan mountains and Mount Everest. And the most famous example of a transform is the San Andreas Fault. So that is in California. So most of you have probably heard about that. Let me go back one slide. Go back one, and you can see here, Ohio is located pretty much in the middle of the North American plate. So it's not at one of these plate boundaries. So you probably wonder why we have earthquakes here, and we're going to talk about that. But before we go ahead, I want to show you a short little video about one of our favorite types of plate boundaries, of the convergent and subduction. So here we go. Okay, so now we're going to move forward and talk about earthquakes in Ohio. So Ohio may not be known around the world as a hotspot for earthquakes, but we do have quite a few each year. And as of yesterday, there's been a total of 535 earthquakes that have been reported since the first event all the way back in 1776. And there's some really interesting fun facts about Ohio earthquakes. The first one is that one of the first seismograph stations in the country was established at John Carroll University in Cleveland in 1900. So that was a really long time ago that we were able to start detecting earthquakes. And from 1977 to 1992, there were anywhere between 9 and 14 seismic stations operating in Ohio due to the John Carroll Network. But in 1999 is when things really started to change. And that's when the Ohio Seismic Network, known as OhioSeis, was formed by Dr. Mike Hansen. And since then, we've been locating earthquakes for the state. And what I wanted to show you, as you can see from the map on the left, there's been quite a few earthquakes in Ohio, but what you'll notice is that they're clustered in two specific areas. So the first area is the Antiseizure Zone, for those of you that live in Western Ohio. And the second area is up by Lake Erie, and that's called the Lake Erie Seismic Zone. So we're going to talk a little bit about that, and we're going to talk a little bit more about Ohio's earthquake monitoring. So the main question a lot of people always ask is, why do we have earthquakes in Ohio? And the reason for that is because we have faults. And I'm going to show you a short little video about faults. And as you can see, a fault is a vertical or non-vertical fracture on the earth where the ground has moved. So there are different types of fault, but the strike slip variety is most common in Ohio. So we're going to watch a short video of what happens during a fault, when a fault moves. So obviously this scale, because that would be pretty terrifying, but we do have small movements deep in the earth that do cause movements and earthquakes. So we're going to go to the next slide. So in 2016, the Ohio Seismic Network transitioned to a real-time monitoring network with automatic detection, location, and magnitude determination of earthquakes. Prior to this, during the Mike Hansen network, we relied heavily on Ohioans to call in and report earthquakes they had felt. And for larger earthquakes, the United States Geological Survey would have detected them. So we were pretty limited up until 2016. So after 2016, we installed about 21 seismic stations throughout the state. And you can see those are the green triangles on the map. The other triangles are other organizations that cooperate with us and provide us data to help us better locate earthquakes. So here we go. So this is basically what a seismometer does, is it records ground motion. And as you can see, you have seismic waves passing through the earth, and they are recorded on the screen for us. So what else is interesting is that we use digital seismometers, and as you can see, kind of like Krista's setup, we use solar power and batteries to keep these units operating in remote parts of the state year-round. And the seismometer, which looks like a coffee cup, is buried underground to keep quiet so that we can record earthquakes. So I thought it would be interesting to show you guys a little bit about our recent earthquake recordings. So as you can see on this slide, prior to 2012, the Ohio Seismic Network was really unable to detect any earthquakes below magnitude 2. And just for a frame of reference, typically a 2.5 magnitude earthquake is about the smallest earthquake that can be felt. And that's under like ideal conditions. Like if you were sitting in a rocking chair on a quiet night with like no car traffic or wind or any distractions like your television or video games or the radio. When we added in these seismic stations, starting in 2016, we were able to start detecting smaller and smaller earthquakes down to below 1 magnitude, which is really astonishing. And basically, had we not installed those seismic stations, we wouldn't have been able to detect these earthquakes that were occurring, which is excellent. So I wanted to talk a little bit more about the Antiseizure Zone that I talked about a few slides ago. And it's famous because it's the site of Ohio's largest earthquake. And as you can see on here, I have some pictures from the St. Louis University archives from the Ohio's largest earthquake, which occurred near the village of Anna on March 8th of 1937. The event was a 5.4 magnitude and had a modified Mercalli rating of 7 to 8. So the earthquake knocked groceries off shelves and toppled chimneys and did so much damage to the Anna High School that it had to be torn down and rebuilt years later. Since the early earthquakes in the Antiseizure Zone in the 1930s, we've recorded over 40 earthquakes, and we even detected 2 really small earthquakes this year, right near the epicenter of the 1937 quake, which shows that it's still active. Our second seismic zone is the Lake Erie Seismic Zone, and it's our most active seismic zone in the state. The largest earthquake in the Lake Erie Seismic Zone occurred in 1986 in Lake County and had a calculated magnitude of 5.0. And as you can see from the image, it's an old image that's black and white, but I highlighted the broken glass windows that happened during the earthquake. So just imagine like you're sitting in class and your windows just shatter. And most recently, there was a 4.2 magnitude earthquake that occurred in 2019, but there was no damage for this earthquake. So some of you may have felt this earthquake if you live in Cleveland area, but most of you, if you live elsewhere, probably did not. But it may have got a lot of news coverage in your area.
Hey, Dan, just real quick question came up here. What's the average strength of an earthquake in Ohio?
You know, we average, I can go back to the slides. 1 second. So, most of the earthquakes, you know, are in that 2 magnitude range. Around there is what we're able to detect most of the time. So in terms of strength, there's really light shaking for most of the earthquakes. It's really rare to have a big earthquake like the one in Cleveland that has, you know, moderate ground shaking. We've never had anything like that 7.8 in California, where it did significant structural damage to a building. So just little things like broken plaster, you know what I mean, toppled chimneys in old houses, stuff like that, little stuff. So,
thank you.
Yep. So I'll move back forward. So again, we had the 1986 earthquake, which did all of the damage to Lake Erie College. And we had the magnitude 4.2 earthquake outside of Cleveland last year, which was felt pretty widely. So, okay. So I put together a cool little demonstration for you guys. I hope you enjoy. So on the left, you can see the ground shaking recorded during the magnitude 4.2 earthquake near Cleveland. The traffic cameras recorded the shaking at different locations, and these are ODOT traffic cameras. So usually they're useful if you're going out for a long drive, but on this day they were useful because they caught the earthquake shaking. And on the right side of the screen, you can see the earthquake happening in real time as it was recorded by a seismic station just to the east of Cleveland, which is pretty neat to be able to see this in real time, because a lot of people don't get to take a look at this. And this earthquake was felt by over 9,000 people, all the way into Canada, you know, in Pennsylvania, Ohio, Indiana. And we got almost 3,000 felt reports within an hour of the event. For us, it's pretty cool because we had 45,000 people come to our website that day to look at the earthquake, and about 10,000 people went to the helicorder page, which is just an image version of what you're seeing on the right over 24 hours. But it was pretty cool to be able to get this footage and put it together for you guys to see what an actual earthquake looks like when it's occurring. So we'll move to the next slide. So now we're going to learn how to locate an earthquake. So I thought it'd be fun for us to locate the earthquake that just happened last year in Cleveland, since it's fresh in our minds. But before we can do this exercise, we need to learn a little more about seismograms. And a seismogram, which is on the right, is the recording of the ground shaking where the instrument is located. So for our case, the image you just saw was in near Cleveland, right? So on this slide, we can see a few different features of the seismogram. So we can see the P wave, which is orange, which is typically a small jolt or light shaking and is normally not felt. Followed by the S wave, which is a larger jolt and usually has stronger shaking, followed by the surface waves, which you can feel depending on where you are. So I want to show you a short little clip. So what you're going to see really quickly is that on the star, that is where the earthquake occurs. And then you're going to see the waves travel through the earth. So if we watch closely, you can see the P wave arrives first, followed by the S wave, followed by the surface waves, right? So this image here looks really similar to what you're seeing over there. And what we want to do in this exercise is we want to identify these different waves and what times they arrive. Right, so we're going to go ahead and move to the next slide. Okay. So now that we know a little bit about seismic waves, we can start the process of locating the earthquake. And like we talked about before, the Ohio Seismic Network has seismic stations monitoring for earthquakes throughout the state. And our first step in locating an earthquake is selecting the stations you want to use. And since we know that there was, shaking on the traffic cams in Cleveland, we're going to pick 3 stations near the city of Cleveland. And to make things easier, we've identified the stations by their color. So station 1 is green, station 2 is orange, and station 3 is purple, instead of calling them by their names. So step 2 is to pick S waves at each seismic station. So this is a example of a seismogram, a 3-component seismogram at station 1, the green triangle. So what do you see? You see the P wave, which arrives at 10:50 a.m. And 48 seconds, so almost 10:51 a.m. And then you can see the S wave, which arrives at 10:50 a.m. and 51 seconds. So if we do some simple math, we can figure out how long it took for the P wave to arrive at the seismometer, and then how long after that did it take for the S wave to arrive at the seismometer. So if we subtract 48 from 51, we get an S minus P time, or the time between the arrival of the P and S waves, of 3 seconds. Okay? And we're going to do this for each seismic station. Okay. So for station 2, we're going to do the same exact thing. So for station 2, the orange station, the P wave arrives at 10:50 a.m. and 50 seconds. The S wave arrives at 10:50 a.m. and 54 seconds. So at station 2, it took about 4 seconds between the arrival of the P and the S waves. Okay. So, and if we do the same thing for station number 3, what we see is that the P wave arrives at 10:50 and 57 seconds, and the S wave arrives much later at 10:51 and 5 seconds. So your S minus P time is much greater, so 8 seconds, nearly twice as long as how long it took. Okay, so moving forward to step 3. Step 3 is to calculate the distance from the epicenter at each seismic station. And this is where things get really interesting. So we're going to use a simple equation that allows us to determine approximately how far the earthquake was from each seismic station. So we're going to start with station 1 and work our way through. So at station 1, the green station, the green triangle, you can see that the P wave velocity is 8 kilometers per second. And that is a constant value that we're going to use throughout this exercise. And the S minus P time is 2.5 seconds, right? So if we use the simple equation distance equals rate times time, then we get a distance of 17 kilometers. So the P wave velocity is our rate, and the S minus P time is our time. So if we multiply those together, we get our distance. So we're going to do that for the next station, the orange station. So if we multiply the P wave velocity of 8 kilometers times the S minus P time of 3.5, we get 28 kilometers. And if we do the same thing for the third station, we get a P wave velocity of 8 kilometers per second, again, times the S minus P time of 8 seconds, which gives us 64 kilometers. So now we know approximately how far the earthquake was from each seismic station. And now we're going to be able to locate the event, which is pretty exciting. Okay. So the farther away the station gets from the epicenter, the greater the time between the arrivals of the wave. So as you can see, that's on the screen. And what we're going to do is we're going to locate the earthquake using this information. So as you can see on the left-hand side, we have a simple diagram of a circle. So half of the circle is the radius, and the full distance across the circle is the diameter. So now we know that station 1 is 17 kilometers from the epicenter of the earthquake, and we can plot this as the radius of the circle. So if we do that, we can see that the earthquake could have occurred anywhere on the circle around station 1. So that's helpful, but if we wanted to, we should add station 2, which will help us get a better location, which is 28 kilometers from the epicenter. So now you can see there's only 2 possible locations, and that is where the circles intersect. So the earthquake is either located somewhere in Geauga County or on the Lake Erie coastline in Lake County. And if we add a third station, you can see that now there's only 1 possible location, and that's where all 3 of the circles intersect. And the red dot indicates where the earthquake actually was. So this location is very close to the location that we calculated in the lab. using almost 20 stations. So it just shows that it does do a really good job of locating an earthquake. And with that, you've located your first earthquake. And I want to thank everyone for coming today. And now we have time to take questions.
I think we've got one here from Aaron Rourke. He said, the question he has is about the lateral pressure from the seafloor spreading in the Atlantic. I understand that minor thrust faulting in Ohio, sedimentary rocks results from this, and I wonder if this results in some earthquakes. I have seen a thrust fault in an Ohio shale road cut near Chillicothe.
Sorry, you broke up. Can you repeat that again?
Yeah. His question is about the lateral pressure from seafloor spreading in the Atlantic. He understands that minor thrust faulting in Ohio sedimentary rocks results from this, and he wonders if this can result in earthquakes.
So in Ohio, most of the earthquakes are occurring really, really deep in the earth, in the Precambrian age rock, which is buried really deep, kilometers deep in the earth. So for my knowledge, there has been no modern day movement of, like, for example, the Ohio shale is probably what he's referencing. So there are examples of faults that are visible in the shale, but those are not the faults that are causing earthquakes in Ohio. These earthquakes are 2 to 3 kilometers deep and even deeper. So.
Okay. Is there a typical number of earthquakes that can be felt in Ohio annually?
So, okay, so this is always a good question for people. So, as I said before, the more seismometers you put out in the field, the lower the magnitude earthquake you're going to be able to detect. So, for example, like, if we put a seismic station in each county, we would regularly detect, really tiny earthquakes. Prior to installing this network, we were recording, from 1770s to 1999. They were recording, 4 to 5 earthquakes a year, right? And just over the last couple of years, we've been recording 30, 40, or 50 earthquakes a year, sometimes more than that. So it just depends on how many stations you have operating. But yeah, really you only feel earthquakes bigger than 2.5.
And I think I have one more for you. I'm just going to read this word for word. I understand that our earthquakes are often due to slippage on deep suture zone. I'd be interested to hear more about the deep structure under Ohio's sedimentary veneer.
Okay, so we have an entire publication called PG23, but just to break it down simply, you had some rifting occurring, millions of years ago. So that means that the North American plate would have been ripping itself apart over in Western Ohio, so the Antiseizure Zone. So you would have had like 2 plates ripping each other apart to form a new plate. So that's kind of a simple explanation of what's on over there. And then you had mountain building going on over to the east. Again, there's more information on that in PG23, so we can share that in the chat window, and we'll give you a much better description of what is actually going on. So I'm a seismologist, and we have a whole team of experts that are petroleum geologists and structural geologists that could probably better answer that question, especially with that publication, which will clearly answer your question.
That is all I'm seeing. Chuck, am I missing anything? in there?
In the questions, I don't think so. I think that was the only other one we had at the moment.
Okay. All right, we want to thank you guys all for logging in. Thank you, Krista and Dan, for doing your presentations. That was awesome. And we've got these all week long. You can log into our site to see what is next, and I believe Chuck's going to share that with you. And tomorrow, I think we're talking about fossils at 2, correct?
We have 2 talks tomorrow, actually. We have
2
one
talks.
at noon and one at 2. Both will be on fossils. The noon talk will be a special lunch and learn on the Columbus limestone and the fossils found there. And then at 2 o'clock, we'll have a webinar that focuses on how you find fossils in Ohio.
That could be fun. So again, thank you all for logging in, and we'll hopefully see you tomorrow.